Hello and welcome to C++ Weekly. I'm your host, Jason Turner, available for code reviews, contracting, and on-site training. This is another PMR episode done in cooperation with Bloomberg, and as always, the views and ideas presented are my own. So this episode, I want to dig into what all of the standard memory resources there are. And you can see here that I have up the cppreference.com page for the memory resource header, as I tend to use. This is my favorite resource for C++ reference material. It's much easier to grasp than looking directly at the standard, although sometimes we do have to go directly to the standard. Now, the memory resources here, we have the polymorphic allocator that came in C++ 17. And the memory resource here is the abstract interface. And we covered this before, but it's got these public member functions, allocate, deallocate, is equal, and private functions that are virtual, do allocate, do deallocate, and do is equal. So if you're going to implement your own memory resource, then you need to implement these virtual functions. But what we want to talk about today are the resources that come with your standard library. And it's actually very simple, but the way that they can be combined gives you a lot of flexibility, a dang near infinite flexibility. And we'll illustrate that right up to the end here in today's episode. So I want to start with the monotonic buffer resource. That's the one that we have actually covered in these episodes so far. So I have up here some space to draw on. So we have the monotonic buffer resource. And this one creates a simple flat memory resource for you. So if we've got one of these, then we just have a pointer to a large chunk of memory. Well, a chunk of memory, however big you originally tell it to make it. Otherwise, it'll grow on its own as it decides. And each time you want to allocate something and put it in here, so if we've got an integer and it goes in here and it takes up this slot, and then we've got some other value, like a standard string, that's in here. Now, recall from our previous episode that if you've actually got a PMR string inside of like a PMR vector or something right here, then you might have the string object itself, and you might have the string data here. And it just keeps growing. Now, if I were to delete this string object right here, the point of one of the things the monotonic buffer resource does or doesn't do, more to the point, is the free operation is actually a no-op. The deallocate is a no-op. So if I were to go and create another string, it's going to allocate it down here. So we just have this one giant blob of memory. And then when we go to allocate something else, like say I want to allocate space for another integer, and I don't have this, it's going to allocate another block for us. And it'll put that right in here. And these will be linked together in some implementation defined way. So it never frees memory until the buffer resource itself is destroyed. And you're always getting contiguous blocks of data for your memory here. And that is extremely important because this is one of the ways that our monotonic buffer resource gives us such good performance. So the next thing that we have is the synchronized and unsynchronized memory pools. So we've got this synchronized pool resource and unsynchronized pool resource. Now, the point is that we have a thread safe version in the synchronized and a thread unsafe version in the unsynchronized. That should be the only difference here. Pool resources, memory pools, work by organizing your memory in different block sizes. With a unsynchronized or synchronized pool resource, we have some sort of allocation table. And then we've got blocks that are going to be done, again, in some sort of implementation defined way, but maybe it's got small objects that are 4 bytes or less in some resource out here. And then it's got something else that's like things that are size 16 or smaller. And so it looks something like this. Now, this is very poorly drawn. As usual, you're used to this kind of quality of handwriting in my episodes when I do this kind of thing. And furthermore, we've got, whatever, pools for giant objects. And it keeps going like this. Again, implementation defined detail. But there are pool options. And we're not going to really spend any time on this, but you can specify when you're creating one of the pool resources what kind of blocks per chunk, largest required pool block, this kind of thing that you want. Now, an important thing to note about the synchronized and unsynchronized pool resources is that they have an upstream allocator, as does the monotonic buffer resource also have an upstream allocator. So with an unsynchronized pool resource, or synchronized, when I call the constructor, I can say, this is my upstream resource. An interesting advantage to this is if we really want all of our data to be in one handy, contiguous place in memory for whatever we're doing with our data structure or our custom allocation, what we can do is give our unsynchronized pool resource or synchronized pool resource we can give it a monotonic buffer resource for its upstream. So we might have our monotonic buffer resource, some very large, I'm just going to let it run off the page, contiguous chunk of memory. And then we've got our pool resource, and it's doing its allocation of blocks of things. And it says everything that's 4 bytes is going to go into here, and then it asks its upstream resource for a chunk of memory. So it'll get this chunk. And then if we do this and say we want objects of size 16, it's now going to get this chunk of memory, etc. And it, ends up creating a big block of memory that has everything that we are doing when this data structure all allocated in one place. So that is the monotonic buffer resource, one large contiguous chunk of memory that can grow. It can append extra chunks of memory onto it. And then our synchronized and unsynchronized pool resources that are capable of freeing things. So let's get back to that. If I have over here a couple events, and I decide to delete this one, destroy it by some mechanism, my pool resource here is going to keep a free list. So it's going to know, oh, you freed this out, so I know that the next time one gets allocated, I can reuse this memory space. So a delete or a dealloc in a pool resource is not a no-op like it is in the monotonic buffer resource. So by combining these two together, we can get the best of both worlds in many ways with the one long contiguous chunk of memory that has all of our data in it, and the ability to free and reuse locations inside of this particular thing. Now, we also have the null memory resource and the new delete resource that we need to discuss. The new delete resource is your default upstream resource. So if you've got a monotonic buffer resource and you give it a local byte array, which we've done that in previous episodes, so that's the constructor for monotonic buffer resource, that this one right here that takes a buffer and a size, and we exhaust that size through the course of using this monotonic buffer resource, then it has to go somewhere for more memory. It's going to go to that upstream, and the upstream is simply the new delete resource. And the new delete resource, it just calls new and delete. That's really not any kind of mystery there. Meanwhile, we also have the null memory resource. And this one is interesting, and we'll play with it in just a minute in this episode. The null memory resource Returns, so this returns a pointer to a memory resource that doesn't perform any allocation. Note that this is a function. We can't directly create one of these. It's some statically defined thing. Its allocate function always throws bad alloc. This is interesting and something that we can use to our advantage in some cases. And its deallocate function has no effect. We also have the get and set default resource. So the default resource is the new delete resource. So in this case, so I've created a standard PMR vector. I did not provide an allocator to it. It's just going to use the new delete resource by default. And we can even see that here, that it has generated a call to get default resource. So this has covered the new delete resource, the get default resource, null memory resource, and we can call set default resource if we want to give some sort of default fallback for any of our PMR types that use a PMR memory resource. They'll just automatically use that default resource for anything that requires an upstream resource of some sort. And again, we'll build on this right now. So what I've done for the rest of the examples for this episode is I've taken this print allocator that was from our friend Rahil that we mentioned in the last episode, and I've amped it up a bit. So now when I do an allocate or a do deallocate down here, we get a fair bit of logging about what exactly is happening. And now what I've done is I've created this allocator that is the default allocator that is our print allocator, but its upstream is the null memory resource. So I mentioned before that we might be able to use this null memory resource to our advantage. And what we can do, this is actually a lot of fun in my opinion. So we set this set default resource here. I'm going to create a vector just like we did a moment ago. And we just see that we just get this message saying exiting main. I have this down here. And this rogue PMR allocation thing doesn't happen. So let's go ahead and do a vector of pushback of 2. And if I push this value back into the vector, it's going to attempt to allocate memory, but I haven't given it a memory resource to allocate from. So when it goes to attempt to allocate this memory, it's going to get the default resource, and we're going to see this rogue PMR allocation. So we could use this as a way to actually track when we're doing allocations that weren't controlled in the way that we needed for our environment. And this throws a bad alloc. So if we try to call the null memory resource allocate, we get a bad alloc. So I'm going to create something a little bit more complicated. Okay, so I'm not actually creating any data yet, but I'm still getting this bad alloc being thrown. And that is because our unsynchronized pool resource or synchronized pool resource, if you recall from here, it has to have its own table of some sort to know where it is allocated data and where it is deallocated data and its free list and that kind of thing. By default, our unsynchronized pool resource is using this default alloc here that tracks our rogue allocations. So let's go ahead and for this moment, give this the new delete resource. So we don't actually see a log message occurring here about the allocation that was required for our table of data that the unsynchronized pool resource has because we don't have an intermediate logger. And we can go ahead and create one of those too. Okay, so we've created our map of strings here, and now I think you're probably starting to see how we can, with great power, be able to layer and combine these allocators and these concepts to be able to get some pretty good feedback as to what's going on. So we can see here that the new delete resource was asked to allocate 528 bytes with an alignment of 8, and it did that allocation at this address. And then when main exits, we get the deallocation. So that is down here on the exit of main. When all of these things are freed, then it's going to free up that memory. Now, if you've been paying attention, we probably should expect that they are going to get a rogue PMR allocation here and a crash, because this string, while it is in fact a PMR string that is going to be constructed, is going to be constructed here with this default allocator. So we get this rogue PMR allocation here, which is awesome. That's exactly what we expected to see. So even though that's a little annoying, it does give us a way to be able to actually trace when and where and how allocations are happening. Now, you may not be aware that standard map actually has an in-place function, just like vector has in-place back. And we're going to take advantage of pairs template constructor, I believe, and see if this does what we want it to do. Okay, so this hello long world becomes just a string literal that gets in place into the standard PMR string, and we can start to now see how the compiler has to do or the runtime that is, has to do an allocation for the pool resources table. And then we now get this pool allocation. This is the first allocation of 80 bytes that's actually being used to store the things that we care about. And then a few more allocations. These are likely because it's creating different pools for different sizes of objects. And, you know, we can, if you really cared, you can trace through each of these things. So you can see how it has to deallocate the pool blocks that were created for the map itself. And then these blocks that were created with the new delete resource on behalf of the pool allocator through its upstream resource. So we can get all kinds of crazy data here. So this is the example that I'm going to leave you with here today, and it's the example that I'm going to leave a link to in the description for this video. And you can also find some of these examples on the official GitHub repository for the channel. So in this one, I am setting up this rogue PMR allocation monitor that we mentioned before. And then I have a top level one that's my out of memory logging resource. So this is its upstream resource is the standard PMR null memory resource. Then I am creating an array of 32K, and I am creating my monotonic buffer resource as my underlying bytes. So all of the data for these examples are actually being stored right here on the stack, 32K available to us. And then we've got our monotonic buffer resource, which is using these underlying bytes. An unsynchronized pool resource, which relies on the monotonic buffer resource. And then another pool print allocator like I was mentioning before. And then in here in my for loop, I am creating a vector that has this pool here. And we can see all the same things that we saw before. We've got the pool allocating from the monotonic array for its own table. And then we've got the various bits of data that are being created by it. And when I get down to these deallocs here, in my pretty print function, we can actually see which strings are being deallocated. And so this is really interesting thing to play with, where you can see exactly what's happening. And also this unsynchronized pool resource drives home the point that memory is actually being freed, because I'm running this through a loop 10 times now. I'm going to get this message from Compiler Explorer. Output truncated right here, because it'll only let us put so much output in a window. But If we were just using a regular monotonic buffer resource without the pool on front of it, this thing would have run out of memory forever ago, because as you should recall, the monotonic resource dealloc is a no-op. It doesn't do anything. And if I were to make this very small, which I'm going to go ahead and do that now, we'll be able to see that we'll get this out of memory error printed and a call to our null memory resource. So really the main takeaway that you should get from today's episode, which is definitely a little bit longer than I intended it to. See, I made it too small for it to even allocate the original buffer. Is that you can, with memory resources, combine these things in all kinds of ways. PMR gives us a huge amount of power and flexibility for tracking and logging allocations and catching stray allocations when we don't mean to be doing them, tightly controlling what we're doing with our memory, and we can combine them, the default ones provided to us, such as the monotonic and the unsynchronized pool resource, into something that is very efficient. I'm going to talk about efficiency in the next episode. So thank you for watching this episode of C++ Weekly.